So at this point, we're close to or past Thanksgiving and nobody's coming onto the campus, and not entirely sure how this is all working, but I don't know that we're supposed to panic. The respiratory system. So we'll talk about all of these bits and pieces, but basically, I want to talk a little bit about respiration to a biologist. Respiration to a biologist is not, it is to a doctor, but it's not to a biologist. Respiration to a biologist is what happens in every cell in the body of something that depends on oxygen. Is that there are actually what they call anaerobic organisms that do respiration, it's still called respiration, without oxygen. So to a biologist, respiration is a process where you move energy from one type of molecule to a more usable type of molecule. And maybe you use oxygen to do it, and maybe you don't. But for us, we do use oxygen, so I'm going to talk about that particular process. What they call cellular respiration, and this is the respiratory system. So glucose was originally constructed most of the time in plants. They took energy from light and used it to build glucose molecules from carbon dioxide. And so the energy that used to be in the light became the glue that holds the carbons together. If you pull the carbons back apart from the glucose, you can free up that energy, and if you're ready, you can put it to use. And what we do is we shuffle it over into a molecule that is much easier to use for energy than this is. This is kind of a complicated thing to pull apart and make use of. When you pull glucose apart, you also wind up with water as just a piece of the molecule that comes out. But ATP, adenosine triphosphate, is almost a universal fuel for the moment kind of molecule. It serves two basic requirements that are not easy to find in something that you can move around in a cell and make use of. It's fairly stable. Right. You could put the energy into something, but if it falls apart pretty quickly on its own, you can't really move it around and use it. But it's fairly unstable, which means that the energy holding it together is relatively easy to free up and use, much more so than glucose. Because it's not super stable, it's one of the things that, I mean, think about all the processes that we do that are kind of centrally located, and then distributed through our blood. That's how glucose gets into the cells, right? It comes out of your digestive system, it goes through your blood, and it winds up in your cells where you put it to use. We don't have any kind of organ that produces and just puts ATP in. It wouldn't last long enough. It's a little bit too unstable to circulate, so every cell is doing this on its own. Some cells more than others, but if a cell needs a lot of energy, we talked about this when we talked about the heart. When a cell needs a lot of energy, it better be cranking out a lot of ATP. Now, other sugars can be used for energy. Other molecules can be broken down and used for energy. We're not going to get into that, but you can use protein and move the energy into ATP. You can use fat molecules, move the energy into ATP. Ultimately, you use an ATP to do the stuff. So your respiratory system has to be a way, sorry, it's one of those mornings. is that this is coming in from your digestive system. This is coming in from your respiratory system. This needs to go out through your respiratory system. And that's the basic purpose of your respiratory system. Get oxygen into your system and carbon dioxide out of your system. Other stuff happens, but that's not the major thing that's going on here. Now, we will work our way into the system from the entrance, but I want to talk about how this all works. Because I got this picture here. Looks like a clump of grapes, right? That's where this word comes from, is that your breathing tubes terminate in these little bubbles. The bubbles are completely surrounded by capillaries, and the inside lining is wet because for oxygen and carbon dioxide to move in and out of the air, they need to move across a wet surface. We talked about that when we talked about babies, is that when you breathe out, you squeeze the air out of these bubbles, and if it was water wet, they would stick together, and we could generate enough energy to pop them back open. But a baby can't do that. But even still, we coat that wetness with surfactant, make the water much less sticky, so it doesn't take as much energy to reinflate it when you breathe back in. But the oxygen and the carbon dioxide are going in and out of your blood right at the very end of the tubes in these little clusters. One of the things that happens if you have emphysema is it compromises this epithelium, and eventually these little clusters, instead of being individual bubbles, become one big fused mass. If you know anything about wax fruit, looks like a clump of grapes, but it's completely hollow inside. Kind of like an Easter bunny, a chocolate Easter bunny. So of course you lose a lot of surface area for oxygen and carbon dioxide exchange when that happens in emphysema. So this is where oxygen goes in, carbon dioxide comes out. It's wet. If something happens that histamines are released in the lining, then the capillaries open up, they get much more leaky, and more fluid accumulates in these things. And they can literally fill up with fluid. And then the oxygen, the air can't get at the lining, it could just get at the surface of the fluid. That's pneumonia. Pneumonia is a symptom. Something is causing inflammation in your lungs, and that's filling your lungs up, literally filling your lungs up with fluid. And but there's a whole list of different things that can do that. If you have pneumonia, then it's a matter of figuring out what have you got that has given you pneumonia. I did talk about when your heart beats. If your lungs are full of fluid, or your tissues are damaged, which can happen with heartworms getting into the lungs and clogging things up and damaging the blood vessels there, then the vessels, the blood flow is compromised. The pressure from the fluid can close them, or they can be damaged. And when your heart pushes the blood into the lungs, a significant amount of it bounces back. It hits that barrier and bounces back and messes with the heartbeat. And that's when they're talking about congestive heart failure. Congestion here is causing failure in your right ventricle. And that's, it can screw up the valves, it can expand the heart muscle, which happens in dogs with heartworms, and just compromise the whole system. Now, the way the system is set up, the air should be going in and out through your nose. Should be. I mean, I primarily breathe through my mouth. A lot of people primarily breathe through your mouth, but actually the system isn't set up that way because the nose has a pretty good function on your incoming air. And what needs to happen is by the time the air gets down here, You don't want it moving too fast. You don't want it under too much pressure, so you don't want to be pushing it too hard when it gets to the very bubbles at the end. They're thin, is that they're fairly easily damaged. So as the air goes through the system, it gets slowed down. In the lining of your nose, you have all of these little curlicues that stick out into the space that do a lot of things, but one of the things they do, they cause a lot of turbulence and it slows the flow of air. When it gets here and it splits into a bunch of tinier and tinier tubes, it slows the flow of air. So that's one of the first things that happens, that needs to happen. Also, the air coming in from outside is not at your core body temperature most of the time, unless it's a really, really hot day. But you need it to be at body temperature when it gets down to your lungs. You don't want to be losing a tremendous amount of heat through all that surface in your lungs. So it's going to get warmed up. And all of these projections into the space are warm. So they're helping to warm the air up, and they're slowing the air down so it's easier to warm the air up. Also, this surface has got to stay wet. You want to do as little as possible to dry it out. So the air, as it goes through the system, it's turbulent, it gets slowed down, it gets humidified. And that's really, really important. I mean, when you're on a really cold day, when you breathe out, you can see how much water is still in the air you're breathing out. That's water you're losing from your alveolar surfaces that you need to replenish somehow. But you're doing that every time you breathe. You can just see it on a really, really cold day. Incidentally, while I'm on the subject, you can see why, if you don't block the access here, that you can spread viruses and respiratory droplets, because the air you're breathing out condenses, but you can see where it's going before the condensation disappears. You're spreading it out and about. Is that next time you're out on a really cold day, notice the pattern around you. You may need a mirror. When you're breathing through a mask, is that you don't get that much out, and what you do get is it gets here and it drops. So the mask is pretty effective at not spreading respiratory droplets with potential viruses in it around you. So that's why it says it's pretty effective at keeping the spread down of a respiratory virus. It works for the flu, works for colds, works for anything that you can spread through respiratory droplets. And it's not a big scientific secret that needs all sorts of evidence. It's just, you just need to think about it. And it's very obvious that it's an effective barrier. It also catches a bunch of stuff. But that's not, hospital masks with fancy valves and stuff, they're in the business of catching things. These masks really are in the business of slowing everything down, more or less, and dropping it near you. And the fact that you're breathing back in air that you breathed out, if you've got enough viral load that you're breathing viruses out, that is not, because people, I'm reinfecting myself. Yeah, you are, but it's not, adding to your viral load is not really doing you any kind of damage. Anyway. Now, the last thing that happens to your air going in is it does get cleaned. Particles get pulled out of the air. I'm going to talk about that more because it happens a little bit more down in your breathing tubes than it does. It does happen in your nasal passage, but not quite as effectively as it does farther down. So the air's going up. By the time you get here, the air's going down. So it hits a curve. I don't know if I got a picture. I think I got a picture of that. Yeah. It's trying to show a little of the folds there. But it goes up, and right here at the very top of the curve is a little patch of sense receptors, chemical analyzers, really. We'll talk about it more when we get to the senses. But the air going around a corner, the particles have a better chance of actually hitting and sticking. It's a sticky surface, hitting and sticking So when you breathe in through your nose, you're gonna pick up chemicals that you can analyze with your sense of smell. And that's how it works. And it is connected straight into the smell processing centers in your brain. If you think you smell something, you go, you bring the air in faster, you bring in more particles, they're going faster, they're more likely to hit that lining trying to go around the corner. And that's why sniffing helps you to pick up smells better. The downside of this is whatever you're smelling, like horse manure. Those are particles of horse manure actually sticking to the roof of your nose. That's the only way you can analyze them. Well, you can't really see it. In this bone, for a lot of people in this bone, for most people in this bone, there are spaces in the bones. It does vary a lot from person to person. Those are your sinuses. Why they're there, a lot of theories. Probably the best theory is that if it was solid bone, your head would be a lot heavier, and you got to hold it up on this neck, so it may lighten the load of your head. People think it changes the timbre of your voice. It's a resonating chamber. I don't know how well the support is for that. But here's the weird thing about sinuses. They are connected to your nasal passage. There are little holes between your nasal passage and those bone spaces. Then blood vessels and nerves run through those holes. Now, in some people, the holes are big, and air and other things can actually go in and out of your sinuses from your nasal passage. In other people, the hole is really tight, the blood vessels and the nerves barely fit through it, and nothing gets through. Like, I never have any kind of sinus problems because I would assume my sinuses are too well sealed. Nothing that is causing problems in my respiratory system get into my sinuses. And some people, in some bones, I've looked at a lot of bones from live people when I used to teach anatomy and physiology. We had 900 students a semester coming through the labs. There were a lot of bones. And it's interesting, this sinus is huge in some individuals and non-existent in other individuals. And didn't really get a chance to see the other ones, but when you, in anatomy and physiology, when you look at a head, they've always cut the head off, the top off, so that you can look inside the brain case. So you get a chance to see that sinus, or see that there's nothing there. Obviously, this is an entry point for a lot of things that are bad for us. So the lining, a lot of cells that produce histamines, a lot of cells that respond to invaders on the surface. Early in your life, your system has got to kind of sort through what's legitimately something that needs to be reacted to and what doesn't need to be reacted to. And the theory is that if you don't expose your system to real invaders, it will start to look for invaders in things it should have ignored, like pollen that you've been breathing for, ever. Some people's immune systems will go, well, we're going to treat that like it's an invader. I don't know if it's like practice or, there is some indication that your immune system needs practice in order to function properly later in life. But, hay fever is a reaction to things you're breathing in that you don't really need to be reacting to. And your system at some point goes, okay, we're going after that. Or dust mite feces, which is what dust allergies are. But those are, it gets onto the cells recognize them as the programmed invaders, produce histamines. Histamines expand the capillaries get leaky, your nose runs, the linings inflame, sometimes irritation makes you sneeze and cough. The coughing's from farther down, sneezing is from up here. And that's how your surface reactions work. They should be defending you against legitimate invaders too. Up. Rats. Your inner ear is here. There is a passageway, a tube from the top of your nasal passage to the chamber behind your eardrum. Those are your eustachian tubes. Coming in from your ear canal, your eardrum completely closes off the canal. It's completely across the tube, and air can't get past it unless you've had some sort of damage. But when you hear stuff, if the pressure around you changes, and keep in mind our not so distant ancestors went up and down a lot of tall trees. If you've gone up and down a hill really fast, or you've gone up and down in an elevator, you know that when the pressure changes, your ability to hear changes. And what's happening is the pressure is, if you're going down, the pressure is higher on the outside and it pushes your eardrum in. If you go up, the pressure's less, and your eardrum with the higher pressure behind it bells out, and it changes what you can hear. That tube that connects this to there, it opens through a little slit into your nasal passage, and it lets air in and out of the chamber behind your eardrum to balance the air pressure on both sides of your eardrum. That's why if you're going up in an elevator and things start to sound weird, that you can wiggle your jaw or yawn. Some people chew gum if they're in the elevator a lot. And what it does is that causes the slit to open and lets the air in or out, because the slit's fairly closed. Now, obviously, other things can get from your nasal passage up into your eardrum, behind your eardrum, which you don't really want stuff up there. But that's where your earaches and inner ear inflammation, well, middle ear inflammation happens. And at some point, a couple of decades ago, because the thing is open more in a lot of little kids as they get more earaches, so more stuff gets up in there, and it's a shorter passage too. And kids that had repeated earaches, they went, let's put, because the problem is pressure builds up from the fluid accumulation from the inflammation. Why don't we put a drainage tube in there? And I don't know why there wasn't anybody in the room going, but isn't that going to make the passageway open all the time if we put a tube in there? And you know what they found out when they put the tubes in? More stuff gets up into the middle ear through those tubes, and so you don't really hear of them doing that much anymore. Another thing right here, I don't think that's actually supposed to be a picture of it. I think that's a dimple. You have tonsils along the lining of your pharynx. You've got adenoids up here, and then you've got a couple more down further. They're not lymph nodes, but they're lymph node adjacent. They're similar to lymph nodes, but they protrude into the space. And in some people, they protrude more than others. And because they are kind of associated with lymph tissue, they often swell up if you have inflammations or infections in this system. Well, the adenoids, if they protrude out too far, block air coming up into your nasal passages. And a lot of our vocal tone is a combination of air coming out of our mouths and air resonating coming out of our nose. If you hold your nose, you know that it changes the timbre of your voice. And for people with large adenoid tonsils, that also tends to give them what we call a nasal voice. So just to let you know. And in some cases, a throat infection will do that to people as well. Well, that's a good place to stop this particular video. We'll pick this up farther down.